Welcome to qnawire.
So they tell us that it is well known, not well known to me, but I guess well known in the industry, that the thermal collection efficiency of a solar collector diminishes with increasing solar collection output temperature. And so as we're basically, um, heating water up or something, and that makes sense, right? As the temperature goes up, then the efficiency probably goes down. So we model that with just this linear relationship. So it is a linear decrease. So we have some coefficients A and B, and so we have a linear. This is the solar collector efficiency, and we have a linear decrease in that the efficiency as this temperature goes up. And then let's see here, the thermal efficiency is a fixed fraction of the Carnot thermal efficiency. Right? So this is some fraction here, and this is the Carnot thermal efficiency. So this is some factor here, some constant. So again, we're basically making some very simple models of things. So this is the of the whatever cycle we have, and so we want our overall efficiency of these things. So we multiply them together. And we just do some math, expand things out, and what they want to know is the temperature. At what temperature should the solar collector be operated at to obtain the maximum overall efficiency? And then what is that efficiency in terms of these constants that we have? So let's see here. We can just do a little calculus here, and we want to maximize the efficiency with respect to the temperature of the high temperature. So we take the derivative of this with respect to TH, plug in our critical value here, and again we just take the derivative here. We wind up with this, and this term are the only things that are left over, and so we get minus B plus A times TL over TH star squared, and that has to be 0 at the where the efficiency is a maximum. And so that tells us that TH star, again, given, well, one interesting thing to note is that F doesn't show up in here. So whatever that is, doesn't matter. Only A and B and TL, obviously. So, these two coefficients and the square root of this thing basically tells us what the temperature is we should be using, heating whatever it is, heating the water up to from the solar collector. Let's see here. Obviously, if A goes to 0, that we don't basically, this should be positive, right? At least, so that A should not be 0. And assuming B is also positive. So again, we can see as if B gets very large, then we just get this huge drop, and so this would be very low. So again, we just need to figure out what these parameters are by looking at doing some experiments. And so then to figure out what the efficiency is, we can just plug this back into here and do some ranging and simplification, and we wind up with F times this square root of A minus square root of B times TL squared. So that is our efficiency, our peak efficiency for this system. So again, it scales linearly with F, and then obviously these other parameters in TL come in, and in kind of a strange way here. But again, if B were 0, we'd say we want it just as hot as we can get it, right? So we want this to go to infinity, and then we'd have F times A would be our efficiency, because T high would be infinite, and so that would be the ideal case. But B is not going to be 0. B is also not going to be negative. If it were negative, then we'd have some weird stuff going on, because we'd have an imaginary temperature, and that would make very, very little sense. So here's what we get for the peak efficiency.